At 6:43 in the morning, the lobby of a mid-rise office building is empty, the floors are clean, the lights are dim, but in the shaft behind the elevator doors, something is already moving. Most people step into an elevator and press a button. They arrive. They exit. They never think about what happened between those two moments, but behind that journey, there is a system, and that system requires constant, invisible attention. There are an estimated 18 million elevators operating worldwide. In cities, they carry more passengers per day than most metro systems. They run in hospitals, in hotels, in apartment towers, in parking structures, silently, vertically, continuously, and every single one of them requires maintenance, not occasionally, not when something breaks, continuously, systematically, on a schedule that most building occupants never see. The people who manage that schedule are called elevator technicians, or in many regions, licensed lift mechanics. They work in teams. They work alone. They work in shafts barely wide enough to turn around in. And they are responsible for a machine that millions of people trust with their lives, every single day. A standard elevator system has hundreds of components: guide rails, counterweights, drive sheaves, control boards, safety governors. Each component wears, each component ages, and each one has a service interval, a window of time within which it must be inspected, adjusted, or replaced. In most countries, this schedule is not optional. It is mandated by law. Elevator safety regulations require certified inspections, monthly, quarterly, annually, depending on the building type, the elevator class, and the local regulatory authority. In Turkey, for example, elevator maintenance is governed by strict standards, including TSE norms and municipal regulations, requiring monthly service visits by certified firms. The technician arrives, opens the machine room, checks the brake system, checks the door contacts, checks the oil level in the guide rails, signs the form, moves to the next building. A single experienced technician may service between 8 and 15 elevators in a single day. The route is planned. The timing is tight. A delay at one building ripples into the afternoon schedule. This is not a trade of emergencies. It is a trade of precision and repetition. But maintenance is only half of the story, because buildings age, and so do the elevators inside them. An elevator installed in 1985 may still be running, but running on technology that predates mobile phones, GPS, and modern safety architecture. At some point, maintenance is no longer enough. The parts become discontinued. The control boards become unrepairable. The safety standards the elevator was designed to meet are no longer the standards that apply. This is the threshold of modernization. Modernization is not simply replacement. It is a systemic retrofit, conducted inside a live building, inside a shaft that cannot always be taken out of service, on a schedule that must work around residents, patients, or employees. A full modernization project may begin with a condition survey, an engineer climbing into the pit and the machine room, photographing every component, measuring every dimension, building a report that answers one question: what can stay and what must go? The control system is almost always replaced. The old relay-based logic, wiring hundreds of individual switches in sequence, gives way to a microprocessor unit, a circuit board smaller than a book that manages every movement, every door command, every floor call. In a hospital, this work cannot stop the elevator completely. There may be a single lift serving an entire surgical floor. Modernization in these environments is staged, one system replaced while the elevator continues to operate in reduced mode, then switched over in a planned overnight window. The drive system, the motor and inverter that control speed and smoothness, is another common modernization target. Older systems used fixed-speed motors. They pulled the cab up at one speed, they stopped it at one speed. The result was a jolt at every floor. Modern variable frequency drives, VFDs, change this entirely. The motor ramps up gradually. It decelerates with precision. The cab arrives at the floor level. Exactly. Not close, not approximate. Flush with the landing. For wheelchair users, for hospital beds, for heavy freight. This difference is not cosmetic. It is functional. Door systems are among the most frequently serviced components. They open and close thousands of times per day. Every cycle stresses the rollers, the tracks, the door operator. When a door fails to close cleanly, the elevator stops. The shaft becomes a sealed column. The cab sits between floors. The entrapment call comes in. A passenger is between floors. The cab is dark or partially lit. The technician on call receives the dispatch. The protocol begins. Not a rescue operation in most cases, but a controlled release. The machine room is opened. The brake is released manually. The cab is inched to the nearest floor. The door is opened. The passenger steps out. Most people never know this protocol exists. They step out of the elevator, shaken, perhaps, and walk away. The technician closes the machine room, writes the incident report, and moves on. Behind every modern elevator system, there is also a remote monitoring infrastructure. Sensors placed on critical components send real-time data to a central server. The door cycle count, the motor temperature, the brake response time. A technician in an operations center can see, from their desk, that a drive unit in a building across the city is showing irregular vibration. This is predictive maintenance. Not waiting for failure, not waiting for an entrapment. Identifying the degradation before it becomes a fault. Dispatching the technician before the passenger even notices. The rope, or in modern systems, the steel belt or aramid fiber, is one of the most scrutinized components. Elevator suspension ropes are not simple cables. They are precision-engineered load-bearing members, twisted to specific tolerances, inspected under magnification for wire breaks, corrosion, or diameter reduction. When ropes are condemned, when the inspection finds them at the limit, they must be replaced. The entire cab is taken down to the pit. The old ropes are removed length by length, each one heavy, each one wound with years of wear. New ropes are threaded through the sheave, tensioned, equalized. Then the system is tested. Again and again. In older residential buildings, towers built decades ago, the modernization conversation often begins with energy. Original hydraulic systems use oil-driven pistons to move the cab. They are energy-intensive. They require a machine room at ground level. And the oil, hundreds of liters, represents an environmental liability. Converting a hydraulic elevator to a traction system removes the oil, removes the ground-level machine room, reduces energy consumption by as much as 60% in some cases, and increases ride quality, speed, and longevity. But the conversion requires weeks of work, and weeks of disruption inside a building that was not designed for that disruption. The residents of those buildings navigate this differently. Some bring their groceries up 8 flights of stairs. Some arrange temporary relocations. Some simply wait, listening to the sound of work in the shaft that runs through the center of their home. In high-rise commercial towers, the complexity scales upward. A single tower may contain 20, 30, or 40 elevator units, grouped into zones: low-rise, mid-rise, high-rise, sky lobby. Each zone with its own control system, its own service schedule, its own modernization timeline. The building operates as a city within a city. The elevators are its arterial network. Managing the maintenance of these systems requires specialized software. Work orders issued automatically when sensor thresholds are crossed. Technician assignments distributed by proximity and certification level. Parts inventory tracked against service demand. Compliance records updated in real time for regulatory audits. The safety governor is one of the components that most people never consider. It is a centrifugal speed detection device mounted in the shaft or the machine room. If the cab descends beyond its designed speed, if the rope breaks, if the drive fails, the governor activates. A mechanical jaw clamps onto the guide rail. The cab stops, within inches. The governor is tested annually in most jurisdictions. The cab is intentionally oversped. The jaws engage. The technician marks the test on the record. This is a system that must work and must be proven to work, even though it is designed to almost never be needed. The modernization of cab interiors is a separate conversation. New wall panels, new flooring, new ceiling lighting, LED illumination replacing fluorescent tubes, longer lasting, lower energy, capable of changing color temperature. In high-end installations, the cab is an architectural space. In standard residential buildings, it is a functional envelope. Both require maintenance. Both age. Both eventually need renewal. There are buildings where the elevator has not been modernized in 30 years. The components are aged. The technology is obsolete. The ride is rough, but the unit still passes its annual inspection. Barely, because the inspection is a minimum threshold, not an optimization standard. This is the gap that experienced technicians and facility managers know well. Compliant does not mean current. The world of elevator modernization is also quietly shaped by energy efficiency mandates. Many urban municipalities now require that older systems meet updated energy standards within defined timelines. This is a logistics challenge as much as a technical one. Thousands of elevators in a single city, a limited pool of certified technicians, a supply chain for specialist components that spans continents. A senior technician with 20 years in the field can tell a great deal about an elevator before they open a single panel. The sound of the doors, the feel of the landing, the way the cab vibrates at the midpoint of a long run. These are diagnostic inputs that no sensor currently replaces. There is a knowledge transfer problem that the industry is quietly confronting. Experienced technicians are retiring. The institutional knowledge, the feel for the equipment, the shorthand of a decades-long career, does not transfer automatically to a digital system. Training programs are expanding. Apprenticeships are being formalized. But the gap between what is documented and what is known is real, and it is growing. Modernization projects also raise accessibility questions that older buildings never considered. Cab sizes designed in the 1970s for standard doorway widths no longer accommodate modern powered wheelchairs or hospital trolleys. Some shafts cannot be widened. The structural core is fixed. This is the negotiation between what a building was built to be and what a building is now required to be. At 11 p.m., a maintenance crew arrives at a department store. The building is closed. The escalators are stopped. But there are 6 freight elevators in the service corridor behind the retail floor, and one of them has not been responding correctly to floor calls since yesterday morning. The technician pulls the fault log from the control board. The error code points to a door zone sensor. The sensor is a small magnetic device, roughly the size of a thumb. It tells the control board that the cab is within the door opening zone. Without it, the system will not open the doors, because it cannot confirm the cab is properly level with the floor. The sensor is replaced in 12 minutes. The elevator runs a self-test. The error clears. By midnight, the freight route is operational again.
That 12-minute repair represented years of training, knowledge of the fault code, familiarity with the component, the right part already on the service van, the right decision, replace, not repair, made without deliberation. This is how invisible systems stay invisible, not through luck, through preparation. In the weeks that follow a modernization project, the system undergoes what engineers call commissioning. Every parameter is verified, every response is timed, the leveling accuracy, the door timing, the emergency lighting. The communication system in the cab, a legal requirement in most countries, is tested against a live response center. The elevator is signed off only when every check is complete. When the elevator is handed back, when the work order is closed and the cab is returned to service, most building occupants notice one thing: it is smoother, it is quieter, it arrives exactly at floor level. They don't know why. They don't need to know why. The system has reset, silently, behind the walls they never looked at. This is the nature of infrastructure maintenance at its best. You do not see it when it works. You only notice it when it doesn't. The maintenance crews, the inspection logs, the overnight interventions, they exist precisely so that the absence of events can continue. That nothing happened this week is the measure of success. Somewhere in this city tonight, a technician is climbing into a shaft, writing in a logbook under a machine room fluorescent, replacing a component that you will never see for a journey you will never think about. The system continues. Vertical, silent, precise. The doors open, you step in, you press a button, you arrive. And somewhere behind the wall, the system has already reset for the next journey. Under this video, there's a subscribe button. It's a small action, but it helps reveal the systems most people never notice. If you're curious about how everyday life actually functions, consider subscribing. And tell us, where are you watching from? Have you ever worked behind the scenes of a system like this?